relative velocity, type 1, shortest distance, B, awkward angles. So in 2005, we had two roads intersecting at an angle of 45 degrees, and we're told that car A is moving towards the intersection with a uniform speed of p meters per second. Now we can see in this diagram that A is coming in from the awkward angle to the intersection, because obviously B is heading west, so it's nice and straightforward, it's on a straight road. So the first thing we're told here in the question is that, the first thing we're told here in the question is that the velocity of car A relative to B is minus 2I minus 10J. So normally we're working out the relative velocity, but in this question we're actually given the relative velocity. And we have to then use that information to try and find the value of P. In other words, what is the velocity with which car A is moving towards the intersection? So if I mark in on my diagram here in A, and I draw my little mariner's compass, I can see that it's going to be going in a southwesterly direction. So it's going to be negative, hence we can see it's minus 10I minus 10J. So we're told that at a certain instance, car A is 220 root 2 meters from the intersection, and B is 136 meters from the intersection. And we're also told that car B has a speed of 8 meters per second. So we're going to use this information, first of all, to try and find out what is the velocity at which car A is moving towards the intersection. Okay, so what do I know? Well, I know that if I'm working out velocity in general, that's going to be U cos A in the I direction, and the velocity times sine alpha in the j direction. So we would have seen that in projectiles, we use that a lot. So therefore in this case, well, what have I got? Well, the velocity of car A is going to be its velocity, which is P, times cos alpha. Well, the angle which it's heading towards the intersection is 45 degrees, but that's in the negative direction for I, and also it's negative direction for J. So therefore the velocity of A is going to be minus P over root 2I minus P over root 2J, because cos 45 and sin 45, both of them equal 1 over root 2. So now we have the velocity of A in terms of I and J, and that's going to be in meters per second. Well, we know the velocity of B is heading in a westerly direction, so that's going to be minus 8I plus 0J meters per second. So therefore the velocity of A relative to B, again page 51 in our maths tables, tells us that that's going to be the velocity of A minus the velocity of B. Not 51, sorry, page 50 in our maths tables. Okay, so therefore if I sub in there the velocity of A relative to the velocity of B, well, A is minus P over root 2I minus P over root 2J, and that's going to be minus B, so that's minus 8I. So therefore that's going to be minus 8I, which is going to give me plus 8I. And if I group the i's, then I have 8 minus P over root 2 in the I direction minus P over root 2 in the J direction. However, up here in the question, we were told that that relative velocity is actually minus 2I minus 10J. So we say, but the velocity of A relative to the velocity of B is minus 2I minus 10J. So therefore, if I equate both of those, well, that's going to allow me to work out what P is. So I can say that 8 minus P over root 2 in the I direction minus P over root 2 in the J direction must equal minus 2I minus 10j. So by equating like with like there, I can see that 8 minus p over root 2 must equal minus 2 if I equate the i's. Or I could equate the j's, and therefore the coefficients would also be equal. So it doesn't matter which I use here, because obviously we've only one unknown, so we're going to end up with the same value either way. So in other words, I have p over root 2 is equal to 10, and therefore p would be equal to 10 root 2, and the same here, p is equal to 10 root 2. So it doesn't matter which way I use. So I only had to find p for part 1. So now we know what p is. I can therefore say the velocity of A is going to be minus 10 root 2 over root 2, which is just minus 10I. And then I have minus 10 root 2 over root 2, which is actually minus 10j. Okay. All right, so go back to the question here. And part 2 says then, how far is car A from the intersection at the instant when the cars are nearest each other? And again, we have to be careful because it says give your answer correct to the nearest meter. So to find out how far car A from the intersection is, well, we're going to move car A to the intersection. So we're going to have to take A and bring it all the way down to the intersection and see where is B at the time it's taken A to move the intersection, and then I can work out the shortest distance using my diagram. Okay, so I'll go on to the next slide for this. So what we want to do is move A to the intersection, get rid of that awkward angle. So to move A to the intersection, well, we know the velocity of A is 10 root 2. We know that the distance it has to travel, so the distance it is from the intersection is 220 root 2 meters. So if we go back to the question there, you can see at a certain instant, car A is 220 root 2 meters from the intersection. And I want to know is how long does that take? So we know that speed is equal to distance over time. So therefore the time must be 220 root 2 divided by the velocity, which is 10 root 2. And therefore that means it takes 22 seconds for it to reach the intersection. Okay, so now we need to know, well, what has happened to car B? So we say, where is car B in that time? So in 22 seconds, how far has car B moved towards the intersection, or has it even gone past the intersection? So we know the car B is moving west at a speed of 8 meters per second. So in 22 seconds, how far has it actually moved? Well, again, we know that velocity is equal to distance over time. So therefore, our distance travelled in that time is going to be the velocity, which is 8 times the time taken, which is 22 seconds. So it has travelled 176 metres in that time. Now, how far away was car B from the intersection? So if we go back to the question, we can see that car B was actually 136 metres from the intersection. So if it takes 22 seconds for car A to reach the intersection, and car B has moved 176 metres in that time, well, what's actually happened is that car B has actually passed the intersection. So we say car B And how far past the intersection has it moved? Well, 176 minus 136 is 40 metres. So 40 metres past the intersection. Okay, so now we can actually draw our diagram. So let's go on to the next slide then for our diagram. So this time B is actually past A. So we're going to have B here on the left, A at the intersection. And if we have A past the intersection, well, what's the distance between them now at this point? Well, B has moved 40 metres past the intersection, so there's going to be 40 metres between them. The relative path, well, where was A going relative to B? Well, A relative to B was going to be minus 2I minus 10j. So again, if we draw our little mariner's compass at the point A, minus 2I means west and minus 10j means south. So we're going in a southwesterly direction. Of an angle theta. And I broke my traditional rule of always working out my magnitude and direction first. So if I go back to the slide, I can see obviously I have my 10 minus 2I minus 10j is my velocity of A relative to B. So let's work out our magnitude and direction here now so we know what theta is going to be. So normally we always do this at the start, so sorry about that. So we have minus 2I minus 10j. I was getting distracted by working out my P. So therefore my magnitude is going to be using Pythagoras. So using my Pythagoras, I have my A squared plus my B squared. And therefore that gives me a magnitude of the square root of minus 2 squared plus minus 10 squared. So that's 2 root 26 meters per second for my magnitude. And of course I need my direction now. So that's my relative speed. So for my direction then, of course, we have tan theta is our j over our I. Or in other words, our opposite over our adjacent. So 10 over 2 gives me 5 for tan theta, and therefore tan inverse of 5 gives me an angle of, it's going west in the I direction, 78.69 degrees in a south direction. Okay, now also for neatness we actually kind of prefer to do opposite over adjacent, and therefore my hypotenuse works out to be root 26, and therefore that allows me to write down that sine theta is my opposite over my hypotenuse, so 5 over root 26, and cos theta is my adjacent over my hypotenuse, which is 1 over root 26. So we want to use that now to work out our shortest distance. Okay, so magnitude and our direction. All right, so back to our diagram then. So B is 40 meters from A. The velocity of A relative to B is going in a southwesterly direction on an angle of theta, and therefore the shortest distance is going to be that perpendicular distance from B to the relative path. So therefore that is 90 degrees. And then if I'm looking for my shortest distance, well, my shortest distance is this value here, d, whereas x is the relative distance. So we say d is our shortest distance, whereas x is along the relative path. So therefore that'll be the relative distance along that path. Okay, so to find our shortest distance, well, we have theta, so d is the opposite, x is the adjacent, 40 meters is our hypotenuse. So therefore d is going to be equal to h sine theta, because of course sine theta is equal to the opposite over the hypotenuse. So therefore for our shortest distance d is going to be equal to 40, our hypotenuse, times sine theta. And we've said over here that sine theta is 5 over root 26. And therefore that simplifies down to give us 200 over root 26, and that's in meters. So now we have the shortest distance. What we need to know is, well, at what time are they nearest to each other? So to find out at what time they're nearest to each other, we need the relative distance and the relative speed. So we've already worked out our relative speed over here on the right-hand side. It's 2 root 26. So therefore, to get the relative distance, we can see that it's going to be our adjacent and our hypotenuse. So we say the relative distance, x, is equal to h cos theta. Because, of course, cos theta is your adjacent over your hypotenuse. So therefore, our relative distance is equal to our hypotenuse, which we said was 40. And if I go back, here on the right-hand side, cos theta was 1 over root 26. Or, of course, you can use cos 78.69. So that's over 1 over root 26. So our relative distance is basically 40 over root 26 meters. So that's our relative distance when they are nearest each other. So therefore the time is going to be our relative speed is equal to our relative distance over the time taken. So therefore the time will be equal to the relative distance, which is 40 over root 26, and that's divided by the time taken, and we said the time taken was 22, sorry, not time taken, relative speed, I should say, so that's 2 root 26, so therefore the time is 20 divided by 26 there, which is 0.769 seconds. So that's the time it takes until they are nearest. Okay, so now we need to know, well, basically how far has A moved in that time, okay? So we know then for A, well, A has already been moving 20 seconds. So therefore, the time it's spent moving is going to be 20 plus 0.769. So that is going to give us t is equal to 20, sorry, not 20 seconds, it's already moving 22 seconds, I should say there, sorry. 22 seconds. So 22 plus 769 seconds. So therefore for A, if it's been moving 22.769 seconds and velocity is equal to distance over time, then our distance is going to be the velocity, which we said was 10 root 2 for A, times the time taken, which is 22.769, and therefore that means it's been moved a distance of 322 metres when they are nearest each other. Now we know that if we go back to the start, that A was actually 220 root 2 metres from the intersection. So therefore that means that but 220 root 2 metres from the intersection at the start. So where is A now? Well, A is now going to be 11 metres from the intersection. Okay, so in terms of marks, if we go back to the start, well, we have velocity of A relative to B. So if we're writing down our equation, we had 5 marks. By equating these two, we had 5 marks. For working out what P was, we had 5 marks. So we had 15 marks just to work out P. And then we had another 15 marks going for part 2. So we had to work out 7.84. So for getting AX, so our relative displacement, we had 5 marks. For getting the time, we had 5 marks until they were nearest each other. And then for getting the 11 metres, we had 5 marks. So there's a lot of bit of work in between there, obviously, to get your magnitude and direction. So they weren't actually given marks for magnitude and direction this time, because obviously we had to work out P. So in total, that question was 30 marks. So again, even though there was a lot of work there, it's all very normal, straightforward work, which was 30 marks. So very nice, again, 30 mark question. Okay.